Right, today we're going to start our third unit, and our third unit, the first chapter is on electromagnetic radiation. So today we're going to figure out what it is and what the different types are. Just before we get going, the first thing to kind of keep in mind here is that our electromagnetic radiation now is just a continuation of our last unit on electricity and magnetism. So if we remember that Ørsted, he used the first hand rule to figure out that if you have a moving charge or some sort of current going down a wire, that it would produce a magnetic field. So remember, if we have, say, a current coming out of the page, we'd use our first hand rule to figure out that our magnetic field then goes around it clockwise. Then Faraday, his was the reverse. So this is if we actually push a wire in a magnetic field. So let's suppose our magnetic field is going inwards. He used the third left-hand rule. Then our thumb would point to the right. Our B is into the page. So our force goes downwards. So we know then our current has to be going down the wire. So those two guys sort of are key to sort of figuring out that electricity and magnetism are tied together. An electric charge moving creates a magnetic field. And a moving magnetic field then will produce a current. So later, a guy named James Clerk Maxwell, he came along further and tried to figure out how these two are connected. And basically, the key to his discovery is that an electric field will produce a magnetic field and vice versa. So the only trick is that the object had to be accelerating. So remember, in terms of acceleration, we either need our speed to change, so we would have our VI to VF, so let's suppose we have some sort of acceleration that way, or it could be just direction. And that's quite often what we do for regular electricity. So in terms of current going up and down a tower, for a cell phone tower or something, it's just changing directions back and forth. So that's what's creating our electro and magnetic fields. So because they're connected to each other, the idea is we're going to keep them tied together, so we call it EMR, electromagnetic radiation. Radiation just means they're going to go outwards from the source, and then EM to combine the electricity and the magnetism. So Maxwell came up with 5 key ideas, and they were later proven. And he predicted that due to EMR, he said that we would get them anytime we have a charging acceleration, which we did on the last page. Then he said whatever these charges vibrate at, so let's imagine sort of an electron vibrating back and forth, whatever that frequency is, that would also match the frequency of the EMR, which makes sense. He then, probably another key one is, he then figured out that the speed, all EMR travels at the speed of light. So he was the first to sort of picture speed of light as being a source of EMR. So light, X-rays, ultraviolet, all these different types are types of EMR, but Maxwell was sort of the first to combine light with that idea. His fourth one is a key one. He says that the EMR travels perpendicular to each other. So if we go back to this previous page, you can see in the bottom here the red is sort of representing the electric field, so it's going up and down. The blue magnetic field is going in and out of the page, and you can see the wave is traveling to the right. So Maxwell said all of these things are perpendicular to each other. So the electric and magnetic have to be perpendicular, and also perpendicular to the direction it's traveling. So it's kind of like our third left-hand rule again. And he said that anything that a transverse wave does, so everything that we've been doing in waves in Physics 20, he says EMR will follow all of those same things. And we'll get to those over the next few days. Because electromagnetic radiation can be a transfer of energy, that's what we're using to transfer energy, we got to think of anything that transfers energy typically is an EMR wave. So in terms of using your remote control, that's EMR radiation. And even though visible light is what our most common one is, because we can see it, there are all other types that have different frequencies, different wavelengths. But the key thing is, because Maxwell said everything travels at 3 to the 8, then they all have the same speed. And if we look at the spectrum, we're going to go through from largest wavelength to smallest wavelength, or lowest frequency to highest frequency. And we're going to just see that visible light is a tiny portion of that. So our EMR spectrum, typically we go from low to high frequency. So that means that the wavelength is reversed. We're going from large to small wavelengths. You can see here our wavelength, radio waves are big, and at the other end of the spectrum, gamma radiation is quite small. And you can see with frequency it works the opposite. So for radio waves, our frequency is quite small, and gamma rays quite large. The other ones on this chart is really not that big of a deal, but sometimes the size is kind of a key idea to kind of keep in mind. So a radio wave is the size of like a huge building. Microwaves the size of your height, roughly. And then you can see it gets smaller and smaller as we go on. So we'll quickly go through each of these. There is a spectrum below radio waves, and they're usually sort of man-made, low frequency kind of waves. We're not going to worry about them. Typically we start at radio as sort of being the first. And this is radio, radar, TV, any kind of signal, cell phone signal, anything like that. Pretty low frequency, pretty safe radiation. And basically how they're created is we just have the radiation has electrons going up and down a tower. So cell phone tower, your electrons just go up and down and they just vibrate back and forth up and down the tower. And that's what creates the wave that the receiving radio or cell phone or whatever picks up. The next ones we're going to look at are microwaves, and it's kind of a bad name because really they're not all that small, but they're smaller than radio waves, so I guess in that sense they're micro. But in terms of real life objects, they're about the wavelength of your height, so like 1 to 2 meters, so they're quite large. And the reason why microwave ovens work the way they do is that frequency matches the natural resonant frequency. So remember, resonance means if you keep adding energy, it gets the wavelength, and the energy gets bigger and bigger and bigger, and eventually that'll excite the thing. So in terms of a bridge collapsing or a wine glass shattering when it hits the right note, that type of thing. So a microwave does sort of the same thing. It matches the resonant frequency of water, which excites the water, which basically causes it to boil, in essence, which then heats up your food. Okay, so kind of a poor name for it in terms of microwave, but they actually work pretty good, and they're relatively safe. As long as you're not in a microwave oven, you're not going to get any kind of damage from microwaves. And we actually use microwaves quite often to have better quality. So like a microwave is actually a better quality transmission than like a FM radio station or something like that. Back to radio, I forgot to mention that. So if we look at radio and you say you're going to listen to 100.3 on the FM station, that's actually in megahertz. So what that tells you is we have 100.3 times 10 to the 6 hertz. So that's how many frequencies per second. So that's how fast that signal is going up and down the tower. So quite large. Where AM channel, something like say 630 CHED, is actually 630 kilohertz. So you'd have 630 times 10 to the 3, which is quite a bit smaller. So AM typically has less frequency, which means it's a bigger wavelength, which means it typically travels further. Where FM has higher frequency, smaller wavelength, which usually means it's clearer, better quality. And that's why microwaves can be used for communication as well, because it's even clearer yet. They don't work as far for distances, but they get really high quality. The next one on the list is infrared. So you can see we're getting close to visible light. And infrared is basically what we'd consider would be like heat energy. So when you feel the heat off a fire or from a heat lamp or something like that, that's our infrared radiation. And we use nighttime goggles. You can see them on movies where they're looking, army guys are looking at people and they see the image of the person's body or object as colors. So what it's detecting is different levels of heat. So if you looked at a person with heat goggles, usually their heart and their head area would be kind of the hottest, which would usually show up as kind of more like a red color, and then the cooler parts of your body, like your hands and your feet, would be typically like yellowish or something like that. And another device we use quite often are remote controls for TVs and things like that. Those use infrared radiation to send the signal back and forth as well. Next is our visible light spectrum. So visible light, as you can see, it's only just the middle part of what we're dealing with, and the only reason it's special is because we can see it. Every other type of radiation, our eyes and brain can't process it, so we can only see that little sliver of visible light. And you should know from elementary, the colors in the visible light are Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And they go from lowest to highest frequency, or smallest to largest wavelength, whichever way you want to think about it. And the key ones we need to remember are typically the ends. So you want to remember that red is roughly about 700 nanometers. So that means it's 700 times 10 to the negative 9 meters. That's the wavelength. And violet's about half of that, so 350 to the negative 9. And then you can see green is right around 500. It's somewhere in the middle. So you can always sort of compare wavelengths to try to figure out what color it would show up as. The next, just past visible light, is another one that we can't really see but we can feel, and that's ultraviolet. So ultraviolet is the energy that we feel off the sun that gives us suntans and sunburns. So ultraviolet, in terms of wearing sunscreen, usually it says they have A, B, C. So all that is in terms of the ultraviolet spectrum. A is sort of the safer types, B is kind of in the middle, and C is worse. So typically we want to make sure we can block those high-end, high-energy UVC rays. Those will be the ones that cause lots of sunburns and skin cancer and things like that. And it's weird that our human body actually needs some ultraviolet to produce vitamin D. So if you live way up north, quite often if you're a kid, you have to take vitamin D pills or drops to help you supplement your body making it if you're not in an area where there's lots of sunlight. Our last two are the most dangerous. So we're getting to X-rays now. So obviously X-rays, pretty small wavelength, and they're so small that they can actually fit through the spaces of your skin and muscles and tissues. So that's why we use them for medicine, right? If we shine an X-ray on a person's hand, it'll pass through all of the flesh and muscles and things like that, but it won't get through bones and teeth and things like that. So that's why we can see if a bone is broken or if your teeth are damaged or anything like that when you go to the dentist. And X-rays are okay in low dosages, and if you only get them once in a while, but if you get them over and over and over again, it can cause some damage and cancers and things like that. So that's why usually your dentist leaves the room when they X-ray you, and that's why pilots have to take breaks more frequently, is to get out of those X-rays that they're experiencing in the atmosphere. And the last one, gamma rays. So these are basically what we'd think of as our nuclear bomb kind of radiation. So it's the most dangerous, pretty much super high energy, high frequency, and they're the ones that we use sometimes for good uses in terms of killing cancer. So people that are getting radiation therapy usually has a mild dose of gamma rays to try to kill that. And if you watch the Avengers, it's gamma rays that make the Hulk, right? So there you go. So a couple of key things with the spectrum is you want to remember, let me just zoom in on this little chart here. So if you're looking at the chart, you want to remember that on the start of it, we have low frequency, and on the other end we have high frequency, and that typically coincides with energy. So radio waves, low energy, pretty safe. Gamma radiation, high energy, quite dangerous. So that's a good way to sort of remember it. And then some people forget where infrared and ultraviolet is. Just remember infrared is on the red end of the spectrum, so Roy G. Biv, and ultraviolet is on the violet end of the spectrum, and then microwaves and X-rays kind of in between. So you'll need to know the order, and you have to kind of remember where's what. You don't need to remember the numbers so much, but mostly just the order. And that's it for today.